Welcome to the Discrete Universe podcast.
Glad to be here.
Today we're diving headfirst into some of the really deep, persistent mysteries in physics. The kind of stuff that fuels Nobel Prizes and probably a lot of late-night coffee.
Absolutely. We're talking about that ultimate quest, aren't we? The search for a unified theory of everything.
Exactly. A single framework that somehow makes sense of the whole universe, from the tiniest subatomic flicker all the way up to galaxy clusters.
Yeah, it's often called the Holy Grail, right? Trying to reconcile general relativity, gravity, the big stuff, with quantum theory, which rules the bizarre world of particles and forces down at the microscale. They just don't seem to play nicely together usually.
And it's not a new problem, is it? I mean, you brought up Hilbert.
That's right. Way back in 1900, David Hilbert, the mathematician, set out his famous list of problems, and his sixth problem was specifically about putting physics on a rigorous axiomatic footing, much like geometry.
Like Euclid's axioms for geometry, but for physics.
Exactly. He felt physics needed that kind of airtight logical foundation, especially to bridge the gap between the microscopic world, like statistical mechanics, and the macroscopic laws we observe.
Okay, so Hilbert called for it. And the sources we're looking at today, especially Daniel Bernstein's paper on quantum geometry dynamics, or QGD, that presents itself as an answer.
It definitely presents itself as a direct response to that call. And it's fascinating because it takes a truly radical axiomatic approach. It really challenges some very fundamental assumptions we tend to make about reality.
Radical seems like the right word. I noticed Bernstein quotes Bernard Werber. What matters is not to convince, but to give something to think about.
Yeah, that sets the tone, doesn't it? It's not about tweaking existing models. It's offering a whole new way to conceptualize things.
It sort of reminds me of that Max Planck quote also mentioned about new scientific truths winning out because opponents eventually die off.
Right. It acknowledges the uphill battle any fundamentally new idea faces. And speaking of challenges, the sources mention Ethan Siegel's points about what any new theory must do.
Which is?
Crucially, it has to reproduce all the known successes of the theories it aims to replace. It has to match observations. All the data GR and quantum mechanics explain so well, QGD needs to explain too.
Okay, so QGD has to predict the same outcomes we see in experiments and observations.
Yes, but, and this is the really key part, it doesn't have to explain why those outcomes happen for the same underlying reasons.
So the what matches, but the why could be completely different.
Precisely. The fundamental mechanics, the assumptions about space, time, matter, they can be radically different. The ultimate test, as both Bernstein and Siegel emphasize, is always the scientific method. Describe, theorize, and critically make testable predictions that distinguish the new theory from the old ones.
Right. And that's our mission today, isn't it?
Yeah.
Especially for you, our physics-savvy listener who might be curious about these alternative frameworks. We want to unpack QGD, focusing specifically on how and why it claims to be inherently a quantum gravity theory based just on the source material provided.
Exactly. It really starts from a completely different conceptual place than the usual approaches to quantum gravity, like string theory or loop quantum gravity.
So where does QGD begin? What's the bedrock?
It starts, just as Hilbert wanted, with a self-consistent set of axioms. That's the foundation. Two key ones mentioned are the principle of strict causality.
Strict causality, meaning?
Meaning the universe only changes state because of causally related events. There's no fundamental randomness or spontaneity allowed at the deepest level.
That's a big departure from standard quantum mechanics right there.
It really is. The other key axiom mentioned is that fundamental aspects of reality are invariant. Their intrinsic properties are conserved. Think conservation laws, but maybe even more fundamental.
Okay, strict causality and fundamental invariance. What are the building blocks based on these axioms?
QGD posits fundamental particles it calls preons. They come in two types, preon plus and preon.
Preons, okay.
And there's a fundamental attractive force called P gravity that acts only between the preons plus. Importantly, these preons plus are considered eternal. Their total number in the universe is fixed and finite.
All right, so preons plus preons and a P gravity force between the positive ones, finite number. Got it. Where does space fit in? Is it the usual empty stage?
This is where it gets really interesting and very different. QGD says space itself is fundamentally discrete.
Discrete, not continuous.
Not continuous, not infinitely divisible. Instead, the sources suggest space is actually formed by the preons. The smooth, continuous Euclidean space we use in everyday physics is just an emergent property, a very good approximation at larger scales.
So wait, at the most fundamental level, Things like position or distance can only have integer values. You can't be halfway between 2 points.
That's the idea. Fundamentally, it's integer-based. This discrete space is also described as being finite in size and crucially static. It doesn't expand or contract on its own.
A finite, static, discrete space made of particles. Wow.
Okay.
And I remember the claims about time were just as radical.
Even more so, perhaps. According to QGD, time simply does not exist as a physical dimension or a physical thing.
Whoa. Okay, spell that out. If time isn't physical, how does anything happen? How do we get change? Physics is all about change over time.
In QGD, change happens because of those strictly causal concurrent events.
Yeah.
Event A causes event B, leading to a change in the state of the system, step by step. It doesn't happen over time. It happens because of the causal sequence of events.
The clocks.
Clocks don't measure time. They just count recurrent physical events or states in some periodic system like swings of a pendulum or oscillations of a crystal. Since time isn't physical, there's nothing physical to measure. It's a concept we derive from observing sequences, not a fundamental part of the universe's fabric.
Okay, my head's spinning a bit. Static discrete space, non-physical time. This changes the entire stage for physics. How do basic concepts like matter, energy, momentum work now?
Well, matter, or mass specifically, gets a very simple definition in QGD. An object's mass is literally just the number of preons plus it contains.
Just a count.
Just a count. More preons plus more mass. Simple as that.
Okay, mass is a head count. I can picture that. What about energy and momentum?
For a single preon plus, its energy E is defined as its momentum P times a fundamental speed C. And the C isn't just the speed of light, it's the fundamental speed limit for everything at this basic level. So E equals PC.
And for an object with lots of preons?
The total energy is just the sum of all the individual preon energies. This leads directly to the equation E equals MC, where M is the total count of preons plus, and C is that fundamental speed.
EMC. That sounds incredibly close to Einstein's E-NC pi, but the sources stress a critical difference. Can you elaborate?
Yes, absolutely critical. Einstein's EMC implies an equivalence, even a conversion possible between mass and energy. Think nuclear reactions. Mass becomes energy.
Right.
In QGD, EMC expresses a proportionality. It links an intrinsic property, the count of preons, plus to the energy associated with that count. Energy is just the number of preons times their intrinsic energy, PC. It's not saying mass can be converted into some other form of energy. The preons plus persist.
Okay, so it's a fixed relationship based on the number of fundamental particles, not a dynamic conversion.
Got it.
Now, motion. Discrete space, no physical time. How does anything move?
Motion isn't a smooth flow. It's described as a sequence of discrete jumps or steps made by the preons.
Like teleporting between points.
Sort of. And crucially, the momentum vector of a preon plus has a fundamental magnitude that, according to the sources, never changes.
Never changes, but things accelerate.
The magnitude of the momentum doesn't change, but its direction can change.
Yeah.
That happens under the influence of forces like gravity or when a preon is bound in a structure. So movement is basically preons hopping between discrete locations, changing direction, but keeping the same fundamental amount of oomph.
Like pixels moving on a grid, but the pixel itself has a constant internal motion value.
Okay.
This is a very different picture. So we have discrete particles, preons, a fundamental force, your gravity, discrete static space from preons, non-physical time. This setup itself is how QGD is inherently quantum, right? Because it's built from discrete units.
Exactly. And it's how it approaches gravity from this quantum foundation.
So look at to the core. How does this framework explain gravity? How did gravity arise from preons and discrete space?
Right. Gravity in QGD is fundamentally an interaction between preons plus. When two objects interact gravitationally, what's happening at the base level is that this interaction is changing the direction of the momentum vectors of the individual preons plus within those objects.
Okay, preon plus momentum vectors changing direction. Is this mediated by a field, like in GR exchanged particles?
According to the sources, no. The interaction is described as acting instantaneously.
Instantaneously. Wow. That's a huge break from general relativity, where gravity propagates at the speed of light.
A massive break. No speed limit for gravity in QGD.
Okay, instantaneous interaction between preons.
Yeah.
Plus. How does this play out at different scales? You mentioned p-gravity, but the sources also talked about repulsive gravity.
That's right. 2GD proposes two aspects to gravity. There's the fundamental attractive p gravity between preons, plus, but there's also a repulsive component in gravity, which becomes dominant beyond a certain threshold distance, labeled day.
Repulsive gravity kicks in at large distances. That sounds aimed directly at cosmology.
It absolutely is. Beyond this distance day, gravity doesn't just get weaker, it flips and becomes repulsive. And its strength increases proportionally to the square of the distance.
Increases with the square of the distance. So the further away something is beyond die, the stronger the push.
Exactly. And the resulting acceleration, being related to the derivative of gravity, ends up increasing linearly with distance beyond day.
A linear increase in acceleration with distance. That sounds exactly like the observations of distant supernovae, the accelerating expansion of the universe.
Precisely. QGD claims this naturally emergent repulsive gravity explains the observed accelerated recession of large cosmic structures without needing to invent something like dark energy. It falls right out of the gravity equation in this framework.
Okay, so potentially no need for dark energy. How about the other big mystery, dark matter?
QGD claims its framework also naturally explains dark matter observations, particularly galaxy rotation curves.
How so?
It predicts a specific distribution of matter within galaxies. Remember, matter is just preons, plus. Visible matter dominates near the center, but further out, the underlying dark preonic matter becomes dominant gravitationally. This distribution, derived from QGD's principles, is claimed to produce the flat rotation curves we see stars orbiting faster than expected based on visible matter alone.
So it explains the observations without needing new, exotic, dark matter particles like WIMPs.
Exactly. It avoids the need for WIMPs or similar particles. And interestingly, it also avoids predicting the cuspy halo distribution that some WIMP models favor, which sometimes conflicts with observations. QGD suggests visible matter is just a form of this fundamental preonic matter. There aren't two different kinds of stuff.
So dark matter is just the normal fundamental matter, preons plus, distributed in a specific way that QGD predicts. That's quite elegant if it holds up.
It's certainly a different approach.
What about cosmological redshift? The main evidence for expansion, if space is static in QGD.
Another fascinating point. QGD proposes that a significant portion of the observed cosmological redshift isn't due to space expanding and stretching light waves.
Then what causes it?
It predicts an intrinsic redshift effect. The idea is that the gravitational acceleration of the light source itself, according to QGD's gravity equation, causes a redshift in the light it emits.
The source's own gravity redshifts its light significantly.
That's the claim. This intrinsic gravitational redshift, combined with the normal Doppler effect from motion, which QGD explains via corpuscular light and momentum transfer, is proposed to fully account for the observed cosmological redshifts. No expansion needed.
That would fundamentally change our picture of the universe's history and scale. Okay, one more big one.
Yeah.
Gravitational waves. LIGO Virgo detects them, seemingly confirming GR's predictions.
Yeah.
What does QGD say?
This is another point of stark contrast. Because space is discrete and static in QGD, it predicts that gravitational waves ripples in spacetime simply do not exist.
But the LIGO signals, they match predictions from merging black holes perfectly.
QGD doesn't deny the signals exist. It proposes alternative explanations for what could be causing those signals within its own framework. The sources mention possibilities like polarized preonic fields, think fundamental magnetic-like fields generated by the preon dynamics during violent mergers, or perhaps even something like dark photons. QGD suggests these phenomena, generated by merging objects, could interact with detectors like LIGO in a way that mimics the expected gravitational wave signature.
So the detection is real, but the interpretation ripples in spacetime versus preonic field effects is different. How could we tell them apart?
That's the key question. QGD suggests looking for effects unique to its predictions. For instance, could these preonic fields affect electron spins in the detector material in a specific way that GR wouldn't predict? You'd need experiments designed specifically to test these distinguishing features.
Makes sense. You need that unique prediction. Let's zoom out a bit. What are some other implications? We touched on light being corpuscular.
Right. Strictly particles, photons as preon plus pairs, and wave-like behavior, like in the double-slit experiment. QGD explains that through the reflection and interaction rules of these particles with the physical structure of the slits in discrete space.
So the pattern emerges from allowed particle trajectories, not inherent waviness.
Essentially, yes. The geometry of the discrete space and momentum transfer rules dictate which paths are possible, leading to interference patterns without needing light itself to be a wave. It aims to resolve wave-particle duality by saying it's fundamentally particles, and wave phenomena are emergent from interactions.
Interesting. And black holes.
QGD predicts they exist are extremely dense, but not infinitely dense singularities like in classical GR. It avoids the singularity. It also offers descriptions for phenomena near them, like potential photon splitting based on preon interactions.
What about the information paradox? Does information get lost?
QGE predicts information is lost in black holes, but this isn't seen as a paradox within its framework, because QGD doesn't assume information conservation as a fundamental, unbreakable law in the same way standard quantum mechanics often does.
Challenging another core principle. It even touches on mathematics itself.
It does, linking back to the discrete reality idea. It suggests that doing math, even abstract proofs, is a physical process requiring energy. This implies proofs relying on continuous infinities might not perfectly map to a fundamentally discrete, finite physical reality. It subtly questions the absolute applicability of continuous math at the most fundamental level.
So the tools we use might be limited by the physics of using them. That's quite meta. How testable is QGD overall, beyond the specific examples?
Some concepts, like velocity relative to the discrete space itself, might not be directly measurable in traditional ways, but the theory claims to provide a framework for measurement. Potential tests mentioned include highly precise one-way speed of light measurements or looking for subtle variations in gravity over vast distances that might differ from GR's predictions.
So finding those edge cases where QGD predicts something uniquely different.
Exactly. That's always the path forward for testing a new fundamental theory.
Okay, let's circle back to our main goal. The how and why QGD is presented as a quantum gravity theory.
Right. It starts with those axioms: discrete reality, fundamental particles, preons, causality. Gravity isn't an emergent property of space-time curvature. It's a fundamental instantaneous interaction between those discrete quantum constituents, the preons plus.
So the quantum part comes from the discrete particle-based foundation, and the gravity part comes from defining the fundamental interaction between these particles.
Precisely. It builds gravity from the ground up using these quantum principles, rather than trying to quantize the existing classical theory of gravity, GR. That axiomatic discrete particle interaction approach is how it's inherently a quantum gravity theory, and it gives a completely different why for phenomena like orbits, lensing, and cosmic acceleration.
It's a complete reconstruction from first principles, aiming to fulfill Hilbert's call for an axiomatic physics.
And that's why exploring ideas like this matters, even if they seem radical. Their attempts to tackle those huge unsolved problems, unification, dark energy, dark matter, by forcing us to question our deepest assumptions about space, time, and reality itself.
It definitely forces a rethink, which leaves us with a really provocative thought to mull over. If time truly isn't a physical dimension, if it's just our way of counting sequential, causally linked events happening instantaneously at the fundamental level, what does it really mean for the universe or anything in it to change or evolve?
Yeah.
Is our perception of flowing time just a large-scale illusion arising from countless discrete, timeless steps?
That is definitely something to think about. A fundamentally different perspective on everything.
Indeed.
Makes you reconsider the nature of becoming itself.
Enjoy more episodes of the Discrete Universe podcast by subscribing.